6.4 Factoring and Solving Polynomial Functions. In today's lesson, we are going to build very heavily on what we already learned about factoring and solving quadratic functions. Now, quadratics are just one type of polynomial functions, and today we're going to take some of those factoring patterns, some of our factoring friends, and we're going to apply them now to polynomial functions of higher degree. So third degree, fourth degree, fifth degree. We're also going to learn about some new friends. So speaking of our friends, remember you have these factoring friends that you worked with last unit. So when we were studying and learning about quadratic functions and how to factor and solve quadratic functions, we learned about 5 methods or 5 different friends. And we are going to revisit these 5 different friends as we move into factoring and solving polynomial functions. And we're going to start with remembering that anytime you are responsible for factoring or for solving or dealing with a polynomial function, think about finding a greatest common monomial factor that you can factor out of the polynomial. Which brings us to example 1, using some of our old factoring friends or methods. So in A, we are given the polynomial function m of x equals 3x cubed plus 6x squared minus 45x. When I look at this polynomial function and I want to factor it, I can ask myself, is there a greatest common monomial? And in fact, there is. All 3 of those terms have a 3 and an x in common. So what I'm going to do is factor out. I can rewrite m of x as 3x times, and now what's left? Well, 3x times x squared would give me 3x cubed. 3x plus 2x would give me the 6x squared. And 3x times negative 15 would give me that negative 45x. Now, I don't think I'm done. I see that I still have a trinomial here that potentially could be factored. It's not a difference of 2 squares. It's not a perfect square trinomial. However, what it is a guess and check. What I need to do is look for factors of the constant whose sum or difference will give me the middle term. So I have to ask myself, are there factors of 15 that I can add or subtract to get 2? And in fact, there are. Factors of 15, well, 3 and 5 are 1 and 15. 3 and 5, I can subtract those to get 2. So continuing along this path of factoring, I can factor it into 2 binomials. First terms are x's. Last terms are going to be 3 and 5. I need a positive 5 and a negative 3 in order for my inners and my outers to give me that positive 2x. So this is factored. And if it just asks you to factor, you can stop right there. Now let's talk about solving this. The reason that we solve is to find our x-intercepts. Think about the degree of this function. This function is a 3rd degree polynomial, so at most it can have 3 roots. Let's find those x-intercepts. So I'm going to set my function equal to 0 because anytime that my output is equal to 0, I'm on my x-intercept. Next, I'll end up using my zero product property. Looks like I have 3 factors here. Each one of them would have to or could equal 0 in order for this product to equal 0. Solve each one of them. Well, the first one, x equals 0. The next one, x equals 3. And the last one, x equals negative 5. So at this point, you guys have a lot of really good information. And I think that you would even be able to graph that. I have all 3 solutions. We said that there would be a maximum of 3 solutions. I have all 3 roots here. This lesson does not ask you to graph yet, but I'm going to go ahead and relate it back to what we were doing when we were graphing. I know about the end behavior of this polynomial function. I know that it's a cubic. I know that the leading coefficient is positive. Therefore, I know it'll be down on the left and up on the right. Now I happen to know my x-intercepts. So one of them's at 0, one's at -5, and one's at +3. My y-intercept also happens to be 0. I now have my 3 roots. I can get a really good understanding of what this graph looks like. I know it's down on the left. It's going to go through my root, down through my y-intercept, maybe back up. I'm not 100% sure exactly where my maxes and my mins are, but this is a pretty accurate graph. All right, moving on to the next one. So again, I'm going to start off by looking for my greatest common monomial, and I'm going to try and factor this. So this function is f of x. Greatest common monomial appears to be 3x squared. I'm going to factor out a 3x squared, and what's left? Well, 3x squared times x cubed is going to give me 3x to the 5th plus 2x would end up giving me 6x cubed minus 6. I don't think there's much more I can do here. If you notice this trinomial here, it is not a quadratic. We do not know how to factor this. However, I am going to give you some tools in the near future to be able to work with this polynomial function and either get some more roots or figure out if there are imaginary roots. So now we'll use zero product property, setting our output equal to 0. Now, I can solve part of this. So I have 2 factors. I can solve the fact that 3x squared equals 0. Now this root, which is a cubic root, at this point we don't have enough tools to solve it, but eventually we will in the near future. So right now I can say to myself, if I divide both sides by 3, I get x squared equals 0. I know in fact that one of my x-intercepts is 0. I probably already knew that because that was also my constant, so that was going to be my y-intercept. I also know some things about this graph. I know that it's an x to the 5th. It's got a positive leading coefficient, so I do know that it will be down on the left and up on the right and go through the origin. But we don't know enough, once again, to find all my roots. We will get to that. Moving on, let's look at C. I am given a polynomial function g of x. It does not appear that every single term in this polynomial has a greatest common monomial. It also does not appear like this is something that I can just use guess and check on. So let's go back to our factoring friends. Let's see, back up here I had something with 2 terms, which was a difference of 2 squares. I can factor it into sum and difference. That's not it. Perfect square trinomial was 3 terms, of which the first term and the last term are perfect squares. That's not it. Guess and check, we've already determined it's not a trinomial. The good old factor by grouping. I have 4 terms. I'm going to group those 4 terms and factor out greatest common factors from each of those terms. Hopefully the greatest common factor from each of those terms leaves me with a common binomial factor. Given that g of x is this 4-termed polynomial, let's hope that I can do some factoring by grouping. Now, when I group these, I like to group the negative sign because that's really a negative 9x. So I'm going to make that a negative 9x plus 18, but realize that there is a positive in between there. This is not multiplication. There were 4 separate terms and I am grouping 2 at a time. And if I decide to make that 9 negative, well then it's no longer minus 9x, it's plus negative 9x. All right, so let's go ahead and start by working on factoring out common factors from each grouping. So in the first group, I noticed that there is an x squared in common. I'm going to go ahead and factor out that x squared. Well, what is left in just that first group of 2 terms? Well, there's an x, and then there's a negative 2. Now let's work on the second grouping. When I factor out my greatest common factor, or my greatest common monomial from that second grouping, My goal is to be left with something that looks a lot like this factor right here. So ask yourself, what can I factor out of there? First of all, well, I see that they both have a 9. Is there a way that I can factor out a specific type of 9 so that instead of having a plus 2 left, I'll have a negative 2 left? In fact, there is. I can factor out a negative 9 and be left with x minus 2. That's super cool because now in both of my groupings, or in both terms, notice I have 2 terms here. Let's use another color. Here's one term. Here's my second term. And in each of those terms, I have a common binomial factor, which I've underlined in green, that x minus 2. Well, I am going to factor out the x minus 2. And then I'm going to ask myself what's left. So I've just like undistributed the x minus 2. X minus 2 times what gives me my first term? X squared. And x minus 2 times what gives me my second term? Negative 9. Now you won't believe this. We're not done. Do you notice x squared minus 9? X squared minus 9 is a difference of 2 squares, and therefore can be factored into a sum and difference pattern. So x squared minus 9 can further be factored into a sum and difference pattern. You want to ask yourself, what's the square root of the first term? That's right, it's x. So x times x will give me x squared. And what's the square root of the last term of 9? That's right, it's 3. That allows the inners and the outers to cancel out and just give you a first and a last term. Awesome, I think that's completely factored, and now it's time to solve. So we would solve this by setting the output equal to 0. Again, when the output's equal to 0, we know we're on the x-axis. Then we're going to take each one of those individual 3 factors and set them equal to 0. So solving each of these, I get the fact that x equals 2, x equals negative 3, and x equals a positive 3. Once again, looking at this polynomial function, I know a few things about it. So if I had to graph it, opposite end behavior, positive leading coefficient, so I know it'll be down on the left, up on the right, a y-intercept of 18. So maybe just a super rough graph here. Again, we're not 100% responsible for this right now, but it's kind of fun to tie it all together. So I've got an x-intercept at negative 3, at 2, and at 3. I've got a y-intercept at positive 18. Let's just pretend it's there. I know that this graph needs to go up, come back down, and then go back up to the right. So starting on the left here, I'm going to go up, come back down, turn around. I don't know exactly where my critical points are, but this is way more accurate than we were on our last lesson. So we're getting there. Completely factored then, if the question is just to factor the polynomial, this will be your answer. If it is to solve, this will be your answer. And if it was to graph, then that graph would be your answer. Again, we're going a little bit above and beyond, but it's super exciting to tie it all together. And even more exciting, you get a new friend. This is so exciting. Quadratic form is very similar to all of your old friends. The only difference is that it's not necessarily that you're going to have an x squared. You're going to have a polynomial where every single term has an even degree and can be factored as if it was a quadratic. So let's go ahead and define quadratic form. Basically means that each term has an even degree. And therefore, we can go back, we can revert kind of to our old factoring friends to help us out. So let's look at q of x. Every term in this polynomial has an even degree. A degree of 6, a degree of 4, a degree of 2. I am going to factor this using some of my old quadratic factoring friends. The first one is there a greatest common monomial? And in fact, all three of those terms do have a common monomial of 4x squared. So I'm going to factor that out. So q of x will equal, let's see, I got a 4x squared. If I undistribute that 4x squared or factor it out, I'm left with x to the fourth minus 5x squared plus 6. Okay, now notice this trinomial right here. So I want you to think about that trinomial. Now imagine instead of looking like that, if it had looked like this. That's a quadratic that you should know how to factor. It's a trinomial. A is equal to 1. Looks like a guess and check to me. Are there factors of 6 that can add or subtract to give me -5? And in fact, there are, 3 and 2. We're going to factor it the exact same way. The only difference is when we think of our first terms, we need to make sure that our first terms multiply to give us x to the fourth. So instead of breaking it up into x and x, we're going to break it up into x squared and x squared. Factors of 6, we just said were 3 and 2. We know that they both have to be negative. I'm going to keep that 4x squared out there because that, in fact, is going to give me one of my roots. It's going to actually be a very special kind of root. We're going to learn more about these later. All right, and so if I wanted to solve this now, I'm going to set q of x equal to 0 because my output needs to be 0. Now I'm going to take each one of those three factors, set them equal to 0, and then I'm going to solve. So I get x equals 0. For this one, I'm going to have x squared equals 3. However, if I take the square root, I'm going to get x equals positive or negative square root of 3. Okay, and then on this one, very similar, x squared equals 2, and then I'm going to get x equals positive or negative square root of 2. Okay, what does all of this mean graphically? Well, this is a 6-degree polynomial. You should know as a 6-degree polynomial that we're going to have the same end behavior, and because my leading coefficient is positive, both ends are going to go up. Now, there are a couple of interesting facts here that you don't know about, but let's go ahead and try and give this a go. All right, so I have roots at positive and negative root 3 and positive and negative root 2. So root 3 is approximately 1.7 and root 2 is approximately 1.4. Okay, that gives me kind of an understanding that I'm going to have some roots at positive 1.4, positive 1.7, negative 1.4, negative 1.7. Now, at most, this polynomial can have 6 roots. Now, let's talk about my x-intercept of 0. My x-intercept of 0, actually, I skipped a step here, right? I had to divide both sides by 4, giving me x squared equals 0. Now, x squared equals 0 tells me this is actually a double root. And what this double root tells me is the behavior of this root. I'm going to try and give you an understanding of what this means. So my x-intercept is going to be 0, and it is a double root. It is also my y-intercept. I know that my end behavior is up on both sides. So I know that what I need to do is I need to come from the left, somehow wrap myself around this x-axis many times, and then make sure that I end by going up to the right. So here we go. And again, I don't know my critical points. Now this double root is interesting. What did I just do? That double root doesn't cross the x-axis. The double root touches it and turns back around. We call that being tangent. And we're going to review a lot more about that in upcoming lessons. So you got one new friend today, and I'll give you a couple more in the next video.